Okay, welcome to this week's version of the homework review. We are talking about Chapter 2, Homework 1, the first part of the Chapter 2 homework, which covers most everything related to atomic structure and electron configurations. Okay, so the averages on this one were a little bit lower than the first one. That's understandable. The material has been becoming more challenging, but I would still say we did very well overall. Now, what I'm going to focus on again are problems where people had a little bit of trouble, and typically the scores for these problems were below 2/3. That means, about a third of you or more got these particular questions wrong, and we just want to address some of the, limitations and things that we have and try to improve for next time. Okay, so we had a question about Hund's rule that many of us were challenged by, and this was, I believe, by a request from a student. So a couple of these questions were requested specifically, and I encourage you to keep doing that. If you have a particular question or topic you want me to go over during these homework reviews, please send them to me at any time during the week, and I will gladly include them. So one of the requests was, nitrogen has 5 valence electrons. Considering the following electron arrangements, which represents the ground state for the N- ion? So we have not specifically talked about ions yet, but we will in the near future. However, it's not too much of a stretch to realize that when we're dealing with the electron configuration of ions, we just need to add additional electrons if it's a negative ion, or we need to subtract additional electrons if it's positive. We learned very early on how to determine the number of electrons in an ion, and now we're just arranging those electrons into the most stable configuration, which we know how to do for neutral atoms, and it's really the same process for ions. So if we're going to do N-, we first consider nitrogen. So nitrogen is atomic number 7, so that means it has 7 electrons. So the ground state configuration of nitrogen, if we look at the periodic table, is 1s2, 2s2, 2p3. Let me pull up a periodic table real quick and review how I got that. So I'll pull up our University of Houston periodic table here. And if we find nitrogen here, atomic number 7, you can see the hand that I'm pointing to it with. So to get to there, we go 1s2, 2s2, that's this block of the periodic table. Now we're in the 2p block, and nitrogen is the 1, 2, 3 atom, third atom in that position. So we have 2p3. So again, use the periodic table to help you do these configurations instead of memorizing all the subshell orders. So now that we have nitrogen, we have to add 1 electron to this to make N-. So if we're making N- now, we're simply just adding 1 more electron. So we have the first 7 electrons, 1s2, 2s2, 2p3. We have 1 more to add. Now the 2p subshell, again going back to the periodic table, any p subshell can hold 6 electrons. There are 6 atoms in the p block, 6 elements in the p block. So you can hold 6 electrons there. So if we're adding just 1 more to make it 2p4, we can still put that in the 2p subshell. We always want to put them in the lowest energy subshell. So this is the configuration for N-. So many of you picked choice A, which is the ground state for nitrogen. Now if we want to figure out which of these is the ground state, we look for 2s2, 2p4. So we need to have 2 electrons in the s, so that eliminates B and C. And so in these two, there's really only one choice that even has the correct electrons in the correct subshell, and that's choice E. Now we should recognize that this is the ground state, because remember, Hund's rule tells us that if we're adding electrons to a degenerate subshell, we add 1 at a time first, and then we have a 4th electron to add that will then be paired up with that first one. So that gives us this arrangement shown in choice E. Alright, we'll talk more about ions next time, but it's really just a very minor extension of how we do configurations for atoms. Positive ions are a little bit more challenging, but negative ions, we just keep adding electrons in the same order that we would add them anyway. Now, another big part of this assignment was the Bohr equation, and there's not a whole lot of equations at this point, but we do have to know how to use them, and very often we're going to use a few different equations in concert with each other, so in combination to solve the problem, and this is one of those. So we're given the Bohr equation here, which is just the equation for a specific energy level. So, if we're just talking about the energy level in a 1 electron atom, remember we have this is the orbital model. You have, the n equals 1, n equals 2, which is n equals 2 is farther away, and so on. All these different, circular orbits, and they're defined by this first quantum number n. They should be circles. I just did a bad job of drawing them. So they should be as we get farther and farther away from the nucleus or higher and higher energy, that corresponds to raising the value of n. And we have this equation here that tells us the energy is a function of n. Now we gave it to you in sort of a funny form here, but the more conventional way to write it would be it's either 2.17 or 2.18 depending on what source you look at. We have this constant here, which is the Bohr constant. Now we're talking about hydrogen atoms, so there is a z squared term here, but z is 1 for hydrogen, so that drops out of this equation, which is why and then finally we have 1 over n squared. Okay, so this equation tells you the energy level for one value of n, but what we're really interested in most of the time is a change in energy that involves jumping between different values of n. And again, if we're going from high n to low n, we're emitting a photon. If we're going from low n to high n, we're absorbing a photon. Now here we're talking about emitting a photon, and so anytime we're talking about changing between two different n values, we want to use this equation here, which is just E final minus E initial. So remember that delta E is just the final energy value minus the initial energy value. So if we take this equation up here and just subtract it from itself with two different values of n, we get minus 2.17 times 10 to the minus, whoops, that should be 18. And then we would have times z squared, which is still 1 for hydrogen, and then 1 over nf squared, so that's the final value of n, minus 1 over ni squared. So what we want to do in this equation is in this problem, we're going to first find delta E using the two different n values. Now, one challenge with this problem is that we're not given the n values directly. So the first excited state, so excited state is a higher energy state, and the ground state is the lowest energy state. So if we're going to the ground state, that means our NF is 1. Okay, so ground state means n equals 1. The first excited state, that's going to be the lowest energy state above n equals 1. Another way of saying that is this is n equals 2. So when you say excited state, you're talking about a higher energy state. I don't know if I used that term in class or not. But ground state is the lowest energy, n equals 1. And then an excited state is going to be anything higher than n equals 1. So the first one would be n equals 2. The second excited state would be n equals 3, and so on. So with those values of n, we can get delta E. Now, one thing you're going to want to become familiar with is how to use your calculator to do exponents, because all these problems are going to have 10 to the minus 18 in them. You have to know the proper syntax for your calculator, and that's been a little bit of a challenge. Just some of you have to get used to a scientific calculator since you're used to a graphing calculator or whatever the case is. So make sure you know how to do that. Don't let that be a problem for you on the exam. So we're going to put in z squared, which is 1 for hydrogen, so that drops out, and then our two values of n. So we're going to the ground state, so nf is 1, and then we're going from the first excited state, so that's going to be 1 over 2 squared for n initial. And so when we do this, we get a delta E of, let me figure this out real quick. We get a delta E of 1.63 minus 1.63 times 10 to the minus 18 joules. Now again, the minus sign tells us that we're going from high n to low n, so that's our delta E, and it's negative because it's an emission process. But what we want to know is the wavelength. Remember, we also have this equation here, E equals hc over lambda. So whenever we're moving between energy levels, whether it's absorption or emission, the energy of the photon that's involved in that process is going to be given by hc over lambda, and it's equal to the delta E that we calculate from the Bohr equation. So if we rearrange this, we would say that lambda is equal to hc over E, and this E here is equal to the absolute value of delta E when we're moving. So the energy of the photon is equal to the difference in energy between the two n values. Photon energies are always positive, so we never want to put a negative wavelength in. That's nonsensical, but it's the same number. So when we do this, we have h times c, so these two constants. Make sure our units are correct. So these are given as joules, seconds, and meters per second. And then our delta E has to be in joules, which it is if we use the Bohr equation. And that should be positive because, again, it's the absolute value of delta E that we care about for this equation. So get rid of that negative sign that I accidentally put in there. And then finally, we just calculate this out. and we would get 1.22 times 10 to the minus 7 meters. And I believe the answer choices on this problem in Blackboard were in meters, so we don't need to convert it to anything else. It's more conventional to give this in nanometers. This would be 122 nanometers, but for the purposes of this problem, we don't have to do that last step. Alright, so this is a very common type of problem. You're going to use the Bohr equation to find the energy difference, and then use the equation for photon energy to determine some parameter, either wavelength or frequency. So in this question, which we also had trouble with, here we're calculating the frequency in hertz. So really it's the same process, but the second equation we use to find frequency is just a little bit different, and actually it's simpler in this case. So we're going to first use the Bohr equation. So we have this Bohr constant. We're going to multiply by z squared. We're still talking about hydrogen here, so that's still 1. And then our n value is here. It's, again, an emission process, so it's going from n equals 4 to n equals 2. So nf is 2. Sorry, let's put that in. Let's go ahead and put that in. So the final value of n is 2, and the initial value is 4. Now, if you switch these two n values, you're just going to get the wrong sign, which isn't a big deal, especially if we're calculating wavelength or frequency, which are always positive numbers. But if you want to calculate the actual delta E value and have the correct sign, you need to make sure you put your n values in the correct order. So we do this, and we work this out. Then we get a minus 4.09 times 10 to the minus 19 joules is our delta E. And then remember that the absolute value of delta E is equal to our photon energy that's going to be involved in this process. In this case, the photon is emitted. And we have an energy equation for a photon. The simple form of it, which we're using in this case, is h times nu. We used the alternative form, hc over lambda, last time. But here we're solving for the frequency, so we just need to use this form of the equation. So we want to solve for nu, which is frequency, and that's going to be our energy divided by h. So the energy, again, is given by delta E that we calculate from the Bohr equation, 4.09 times 10 to the minus 19 joules, divided by h. So we should get 6.17 times 10 to the 14th hertz. Now the units for hertz are seconds to the minus 1, or cycles per second, and that's equivalent. You don't have to. There's no conversion there between those units. They're defined the same way. So we have, this is just a variation of the previous problem, where we're going to use the Bohr equation followed by the equation for the photon energy. Now let's just start to recognize some things. We've been doing a lot of these problems now, and sometimes you can, give your answer at least a partial check just by seeing if the size of the answer is reasonable. So when we do photon energies or delta E's, for atoms, we should get pretty small numbers. 10 to the minus 18, 10 to the minus 19. If you calculate it and you get some huge exponent like 10 to the 20th, positive exponent, that's you probably did something wrong. You want to check your answer. And same for wavelengths. They should all be in the probably the nanometer range is most common. So if you get something way different than that, check your answer. And then for frequencies, we're talking 10 to the 14th, 10 to the 15th hertz, somewhere in there. So again, if you get something way higher or way lower than that, chances are your math was off a little bit somewhere. So always check your answers, make sure they're at least reasonable, even if you don't have time on the homework or the exam to totally do the problem over again and check your answer. Now another application of the Bohr equation is calculating ionization energies for hydrogen. So ionization, we talked about it in more detail last time. That's completely removing an electron from an atom. Now in the context of the Bohr equation, this means that our final n value goes to infinity. So as we said before, as you get farther and farther away from the nucleus, the n value goes up and up. And so if you go to the limit where n equals infinity, that's the limit where you're ionizing the atom, completely removing the electron. So we're just going to use the Bohr equation. Now we want to know, is this gamma ray 1 times 10 to the minus 8 centimeters, does that have enough energy to remove an electron from a hydrogen atom? So the first thing we need to do is calculate the ionization energy of hydrogen. So for this, again, it's the change in energy involved with taking an electron from the ground state, n equals 1, to n equals infinity, which is completely removing it. So we use the Bohr equation. Z is still 1 for hydrogen atoms, so we don't have to have that Z squared term. And then now we have the final value of n is infinity, and then the initial value of n is just 1, the ground state. And so what we get is just the Bohr constant, but as a positive number. So the ionization energy of hydrogen is this Bohr constant, 2.18 times 10 to the minus 18 joules. And that's because this term here, 1 over infinity, goes to 0. 1 over infinity always goes to 0. So you have a infinitely large denominator there. Alright, so that's the ionization energy of hydrogen, and now we want to know, does this gamma ray up here have enough energy to do that? So we're going to calculate the energy for the photon using this equation, hc over lambda. Now one caveat here, when we use this equation, we have to have our wavelength in meters. Okay, 'cause we're getting an answer in joules, that comes from this Planck's constant here. We have our speed of light is in meters per second. And so in order for those meters to divide out, in order for us to have the right units in our answer, we need our wavelength to be in meters as well. So if we have our wavelength in meters is going to be 1.00 times 10 to the minus 8 centimeters times 1 meter, which is 100 centimeters. So that's going to be 1 times 10 to the minus 10 meters. Okay, so here we're given wavelength in centimeters, which is not particularly conventional, but we wanted to see, can we do this conversion and get it into the right units. Okay, so then we put that in. And when we calculate this out, should have done this beforehand so I don't have all these awkward pauses in my videos. Okay, so when we calculate this out, we get 1.99 times 10 to the minus 15 joules, which is much larger than the ionization energy. Okay, so the ionization energy is 10 to the minus 18. Here we're at 10 to the minus 15, so we're, by 3 orders of magnitude, we're much bigger. So this is going to be true then, that is clearly enough energy to remove an electron from hydrogen. Alright, now one last point I want to make about electron configurations is, we need to know how many of each orbital type there are. That comes into play when we're filling the orbitals, and also especially when we want to determine the number of unpaired electrons, and we have to arrange those electrons using Hund's rule into the orbitals in the correct fashion. So the types of subshells we're going to talk about when we do electron configurations are S, some value of N paired with S, NP, ND, and NF. Remember that the S subshell starts with N equals 1, the P starts with N equals 2, the D subshell starts with N equals 3, and so on. But we have S, P, D, and F subshells, and that's going to determine, that value of L, which is the S, P, D, or F part, is going to determine how many electrons can go in there, and so on. So the L value that corresponds to these, again, are 0, 1, 2, and 3. These are the L values you're going to see in real atoms. You could have higher values of L, but only in excited states or in atoms that don't exist yet. And then the number of orbitals is given by 2L plus 1. So for every S subshell we have 1 orbital, for every P subshell we have 3 orbitals, for every D subshell we have 5 orbitals, and for every F subshell, which we're not going to deal with a whole lot, we would have 7 orbitals, and there's 2 electrons per orbital. So remember, this relationship tells us that in an S subshell we can fit 2 electrons, and that's why if we go back to the periodic table, the S block here has 2 elements, or there are 2 columns in it, 2 columns of elements, because there are 2 S electrons that we can place into the S subshell. P, you can fit 6 electrons, and that corresponds to the periodic table having 6 elements in the P subshell, 6 columns there. D, you can fit 10, F, you can fit 14, and again the periodic table shows us that. The D block, this middle part here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements wide. The F block has 14. Okay? So we have, from the periodic table, we can get these relationships easily without having to remember them. But if you remember 2L plus 1, that also tells you the number of orbitals, and then 2 electrons per orbital tells you how many electrons you can fit in there. So when we're filling up orbitals, we need to have this many available depending on what subshell we're in. So that comes into play when we're determining unpaired electrons. So first of all, this is a two-part question. Now Blackboard is very picky about syntax, so we specify that you need to have one space between the comma and the number. Some of you didn't do that. I gave you the point anyway if you asked about it, but please follow the directions as closely as possible, because Blackboard, again, is a computer, so it's not going to give you any leeway when it grades your answer. Now, we want to know which atom this is and how many unpaired electrons there are. Now, to figure out which atom this is, we're talking about a neutral atom in this case. So this is a neutral atom, as it says in the problem. So all you really need to do is count the number of electrons. We can use the periodic table to maybe figure out which element it is, by going through the configuration. But if we just know the number of electrons, that's the atomic number from the periodic table. So in this case, we have argon 4s1 3d5. So argon on the periodic table is atomic number 18. So that means we have 18 core electrons. We have 1 s electron and 5 d electrons. So that means whatever element we're talking about here has a total of 18 plus 6, which is 24 electrons. If we go to the periodic table, chromium Cr is atomic number 24. So that's the first part of our answer. This is chromium because it has 24 electrons. Now this is the ground state for chromium. We talked about this just in class yesterday on Wednesday. Wednesday the February 10th if you're watching this much later on. We talked about how there are some exceptions to the Aufbau principle, and this is one of them, where we get a half-filled D subshell. So now knowing the ground state configuration, this is where we have to determine the number of unpaired electrons. So we only need to consider partially filled subshells, and we have our 4s and our 5d, our 3d, which are going to be partially filled valence orbitals. Now remember, there's 5 d orbitals available because L equals 2. We just saw that in the last slide when I reviewed that. So if we put the electrons in, there's 1 electron in the s orbital, and we have 3d5, and Hund's rule tells us we have to add 1 electron in each orbital, all with the same spin, before we pair them up. So with 5 d electrons, we've put 1 single electron in each d orbital, so we have 6 total unpaired electrons, because one of them is in the 4s subshell, and then we have 5 unpaired electrons in the 3d subshell. So a total of 6 unpaired electrons. So if we were writing the answer in Blackboard, the correct syntax would be chromium, or Cr, comma, space 6. Okay, that concludes this week's homework review video. As always, if there's something I didn't cover, please ask the question in the Blackboard forum or ask me directly. And on top of that, if you have anything in the future that you want me to cover in one of these review videos, I'm definitely open to suggestions, and I will take your desires into account. All right, so thanks for tuning in, and I will see you in class soon.